I am Rob Frazier with HDR, and I have been doing this kind of work for around 28 years. I'm a practice leader for Kentucky and Tennessee for traffic and planning, and turn it over to Adam for introductions.
Yep, so I'm Adam Hedges. I'm a traffic engineer with HDR. I'm in the Lexington, Kentucky office. I've been doing, I guess, traffic engineering related work, mostly operations-based stuff for about 7 years or so, and kind of did a lot of, I pronounce it as Vissim. I don't know if that's my Kentucky accent coming through, but starting in grad school and then kind of working in consulting since. So, yeah.
All right, well, I'll start us off. We'll be going back and forth a little bit, but we wanted to start with the project origin. And as Adam pulls up that next slide, I just wanted to say thank you for the opportunity to present what we're doing here in Kentucky. We think it's hopefully got some value, certainly value here, and maybe value to others as well. So the project started a few years ago. We were working with the Transportation Cabinet, which is our DOT here in Kentucky, reviewing some models. We were reviewing various simulation models and got into discussions with them about how those models were set up and functioning, and that there are multiple ways to do certain things, and it kind of brought up a topic that they had been discussing on and off over the years of setting standards for microsimulation in the state and making sure that they kind of knew what they were getting. And that led to the to the start of a project to develop guidance here in Kentucky. And so the guidance, the next slide shows kind of the three main purposes of these guidelines. Is model consistency. So that was an issue in some of the reviews that we were involved with, and discussions. So just model consistency, making sure we get similar results, and even if different people are doing the work, and then model accuracy, and then streamlining the modeling process so that it is it's effective, doesn't take too much more time than maybe it should. So those were kind of three goals that the cabinet set out for this project. And then the next slide kind of hits home, especially the first two of those. We reviewed, as part of this effort, we reviewed 10 different models, and that were all Kentucky models, and we looked at how different parameters had been adjusted as part of calibration, and the things, the boxes that are in green show things that were adjusted that fell within the range of parameters that we ultimately are recommending for the guidance. And then things that are in red are potentially outside of that range that we would have, we are recommending in the new guidelines. And you can see that there are very different sets of, things were very different between different models. Some folks changed driving behaviors, many did not. They left them as at the default. So that's the gray. The gray is kind of left as a default. Green is within the range that we have in our draft guidance document, and then red would be outside of that range. And you can see across different parameters, there were some very different things being done with the models. And I will say that not all of them are inaccurate or anything. We don't know the context that all of these models were developed for, and that was made clear when we've been talking with KYTC. They're also anonymous. We don't know who did them. We just kind of looked at the fact that there's some considerable variation, and so for improved consistency, these guidelines will kind of give those ranges to start from, including seed files and things that we'll talk about later. So Adam, what else do you want to add on this slide? I know.
No, I think that pretty much covers it. Yeah, just again, the gray is kind of left as default, and no real change from just a base Vissim model. Green is what we would kind of, it's in the realm of what we're recommending, and then red is kind of a change, but not really in the direction that we are recommending. And so you can see that maybe at the bottom there, even the vehicle routing, there's kind of point-to-point and end-to-end used, and point-to-point is not necessarily, again, always in our eyes, I guess, incorrect, but so it isn't exactly shaded red. It's kind of a orange or salmon color, but so it's a little bit of a gray area. I guess no pun intended with half the table being gray, but yeah, that was just, again, there are many different ways to do things, but just another difference in modeling kind of across the board there. It switches back and forth between them. So.
All right, so the next slide, this project focused on Vissim, but it also looked at transmodeler. We reviewed 5 transmodeler models as well. Most of them were left with the defaults for a lot of the key behaviors parameters that we've been looking at, and we just identified that. So for completeness, we want to share with this group that we did look at transmodeler as well as Vissim, and the guidance document addresses both softwares, which those are the 2 that are used here in Kentucky. So not much more to say on this slide, but there are guidance documents like this across the country, and so ours is in development. It's really in draft final form. There are a number of others. At the time that we started this, all the blue show where there were guidance documents. There may be others that are coming online since this map was created, but gives a sense of, we're kind of joining those states that have taken the time to put down how they want simulation done in their state. And the next slide shows a lot of the things that are in those documents as part of the literature review. There's a look at scoping and data collection, and a lot of calibrations in all of them. There's a number of things that are in these documents. Ours covers all of these categories, and then it also focuses on the parameter values. That's really where this presentation is going to go, is what are the things that we focused on for giving guidance on doing setting up models and doing calibration work. So that's kind of where much of the rest of this presentation is going to focus, but the guidance document that we are developing addresses all of these topics and provides folks that are doing simulation work in Kentucky with that information. It also helps those who are at the Transportation Academy who are scoping projects and deciding how to move forward with projects. So analysis tool selection, for example, is part of this this process. So with that, I'm gonna go into just kind of the project was done in 3 phases. The first phase included the literature review, looking at those guidance documents we just showed you, and developed the scoping and tool selection kind of process. And just at the bottom of that phase 1 box, you see parameter selection. That was a big part of what we did, is we determined which parameters we were going to investigate further, do some research on, and come up with ranges for. So phase 2 included a lot of the detailed work of, and talk about this, about getting information and developing parameter ranges and how should folks do calibration. Phase 3 is where we are now, where we have done the pilot project work, kind of looking at other models, and that's what I showed you with those boxes that we were able to color code it, because we kind of looked at those at the end to see how would the parameters that we've developed potentially have affected those models. And then we've got the guidance document, and training is coming up here very soon. So that's and with that, I'll turn it over to Adam.
Okay, thanks, Rob. Yeah, so I guess just another note here on this slide and the project outline. I didn't include this kind of in these phases, but throughout the process, we've tried our best to try to get feedback from both kind of the software vendors. So this guidance is mostly focusing on Vissim and Transmodeler. So we've had a few calls with both PTV and Caliper just to talk about what we're doing, what we're finding, and get some feedback and input about how to go about doing some things. And I'll kind of talk about that as we go. There's been a couple recommendations of how to implement certain findings. But in addition to that, we also throughout kind of in all three phases really tried to get feedback from other modelers in Kentucky, shared kind of what we're finding, what we're doing, had people try to test things. And then in the parameter selection portion, you know, right at the end of phase one and going into phase two. Phase one, HDR is working with another consulting firm to develop that first phase of the project and do a lot of that upfront work. And then, so we were talking with them about it, and then we had kind of an initial model user group meeting with a lot of the microsimulation modelers in Kentucky, where we were talking about the parameters that we were going to look at. So trying to get feedback to see if they thought, you know, hey, these are things that we're changing, these are things that we think are important, or those don't seem important, what have you. So that led us to kind of the parameter analysis portion of the project, which was really a big section, and a section that's a little bit different than what we saw in other guidance documents. So a lot of this next remainder of the presentation is going to focus on that. So kind of like I was mentioning before, we selected some parameters based on kind of three main criteria. So things that we noticed just from modeling ourselves or reviewing models, or the other guidance documents, parameters that were commonly changed in models, parameters that have kind of significant impacts, and then parameters that we thought the defaults in the software might be significantly different from what Kentucky would be. So those are just kind of and/or criteria. So multiples kind of fall into multiple categories, but that was the general framework for how we selected the parameters. And there were 9 that we were really looking at, and of those 9, 6 are really kind of vehicle interaction based, so like actual driving performance and vehicle interaction in the model. So those are graphically tried to depict it on the screen here. So time headway, standstill distance, minimum headway, acceleration, deceleration, and then lane change distance. Those are kind of the 6 that you would be able to kind of physically observe, and then the additional 3 to make the full 9 is listed here, but those 3 at the bottom, 7, 8, and 9, are kind of the vehicle speed ranges, so kind of speed decisions, and vehicle fleet composition, and then truck weight to power ratio. Those 3 are more background or fleet associated stuff that you don't really observe between vehicles in the model, but certainly affect the overall outcome of a model. So that's a full list there on the screen. Many of you are probably familiar with these attributes, how they might affect a model. Maybe you've changed them, maybe you've observed them being changed. So they're commonly referenced in other guidance documents, and people provide values or ranges that they would suggest you use. And for this project, we wanted to make sure that it was, I guess, as local and real world as we could. So our real goal was to use kind of real local Kentucky data to generate or validate the existing values or ranges for each of these parameters. So to do that, we were kind of going about it with a few different analysis methods. The main one and the focus for, again, a lot of this topic is the trajectory analysis. So you can see there, we were able to kind of look at those main 6 using trajectory data, and then the remaining 3, we kind of use different data sets for each, but historic speed data provided by KYTC, kind of historic HERE data on a variety of different roadways, VIN data, so vehicle registration data throughout the state, and then just kind of literature research on studies about weight to power ratios. This one was the least Kentucky specific, but trucks are not different in Kentucky. So we thought that was kind of more across the board normal. So to do the trajectory analysis, this was new for me and seemingly new in general. We collected data using drones. So we collected video footage with drones in 8 different locations, both urban and rural, and on arterials and freeways throughout the state. So we try to get a good mix of different types of driving. Not sure how familiar everyone is with Kentucky, but it is, you know, it has a variety of different environments. It has kind of generally rolling kind of terrain, but it's a very traffic engineer thing to say, but rolling terrain, but urban and rural and suburban sections throughout the state. And so we wanted to try to get a good mix to try to get a better handle on what's actually going on. And we did try to provide urban and rural recommendations where they make sense. But I guess the other piece to that is, to me, it was a question of what does trajectory data mean and how do you collect it and what do you do with it? That's kind of a next step beyond just collecting traffic counts or vehicle speeds. We really are looking for the interaction between vehicles in a network. So what is vehicle A's speed related to vehicle B, and what is the distance between them? How is one lane change? How is someone lane changing as it relates to the other? So that was kind of the newest part of this analysis. And again, like I said, we collected data in 8 different locations, and this was kind of a little bit of the process that we used to analyze that. So we had a sub-consultant collect drone data at intersections, on freeway locations, and on arterials, just kind of hovering above a scene like you're seeing here, and then using another kind of software vendor, analytics company, we were able to kind of upload the videos into their system, and they're able to track vehicles in the video frame as they move through. So you can see kind of in that still, and I have some videos here in a second that show exactly what they're able to track. And then from there, we were able to export all that kind of raw trajectory data that is registered to each separate vehicle and time stamped and location stamped, and do some kind of post-processing just using, you know, analysis tools like Excel to try to determine what is actually going on the roadway as it relates to those parameters we were talking about. So the company we used was data from Sky. So hopefully this is loading on your screen, but there should be just a little video playing. And data from Sky, there are a couple companies that do this. This is a European-based company, but we had kind of researched and talked to a few different vendors for this, and they seemed like they had a platform that worked best for what we were trying to do at the time. But there might be additional ones out there at this point. We started this maybe a year ago or so. So as you can see just in this video, it's tracking all these cars as they move through this roundabout. And here is, again, that intersection that I showed before, just a clip. And you can see here, it's kind of IDing cars as they enter the frame, and then giving each one an ID, and then tracking them as they move through. So I'm going to show 3 videos, each of them kind of showing a different attribute to what this data can do. But it has the ability to also be geolocated. So at first it's just like showing you in pixels, but this kind of jumps into translating it to miles per hour or feet per second. But these 3 videos are from different areas of the state. So this is in Paducah, Western Kentucky. This is in Northern Kentucky on a freeway segment there. So you can see it's catching all these vehicles as they enter, tracking them through, and showing their speeds as they change. And then similarly, this is another video in Louisville, Kentucky. So another kind of urbanized area. And this is showing kind of acceleration, deceleration changes, which are very rapidly changing. So that was kind of the backbone for a lot of this trajectory analysis. And that was the first time we had done that kind of work, and it kind of became at a achievable consumer level. So it really could be done on any project at this stage. Obviously, you wouldn't want to do all this stuff that we're doing for this project, but just in general, it was surprising how easy of a commodity that was. But so we use that data, like I was saying, to kind of come up with some initial findings and recommendations for the 9 different parameters. So I'll kind of run through those parameters in general, showing mostly graphs on the left, and then just some general data analysis pieces on the right, and I'll just talk to each one of them. So looking at the time headway, I guess just really quick before I go through all that, I want to mention that this was both for, like we said, Vissim and Transmodeler. So I'm mostly trying to focus on Vissim here, but there you might see some Transmodeler data on some of these tables or some of these graphs, just because that was the focus of our project, was to accommodate both softwares, to be a bit agnostic toward software selection in terms of microsimulation, and try to make them comparable. So make them both be a little apples to apples. If someone chooses Vissim or someone chooses Transmodeler for the same type of project, we want the results to be something that is kind of cohesive. And the other consideration was, we're getting a lot of output data, obviously. All the observed data is output, and we're trying to come up with input information for both pieces of software. So there's some consideration to that, especially on headway here. You can see this graph. The blue or teal color data bars are all of our observed headway values, and you can see they would range all the way past 3 seconds. But I kind of did a cut there, and you can see it goes all the way down to 0.1. Now, in reality, people following at 0.1 seconds or even up to 0.6 or 0.7, it's pretty tight. You're not really leaving a lot of space in between vehicles, and that's probably not something you should plan for, but it was observed in our data set. So again, we're taking into consideration what's an observation versus what's reality and what we should be programming the models to do. So so for this first kind of CC1 parameter, time headway, this is our data set based on kind of the frequency distribution and the way that it looks as it compares to the default. We were recommending this range of 0.7 to 1.6 to be used for Kentucky models. So yeah, that doesn't rule out the default range. The default is pretty representative of our data, and kind of in that middle of that range we're recommending. So we don't want to exclude that, but we wanted to provide some guidance on either tightening it up or loosening that default range. So kind of moving along, minimum headway, another just similar parameter. It has generally less of an impact from what we kind of talked to PTV about and what we observed ourselves. It's only really used in specific lane changing and vehicle interaction situations. So it's not always enabled anyway, but it's just how close somebody would be willing to get in terms of distance. And as you can see, our values are kind of on par with what the Vissim default is. Vissim default is 1.6 feet. I think that's half a meter. And in our data, we had some of the low end observations were in that 1 to 2 to 4 feet range. So while it's not happening all the time, and while we had a decent sample set, we didn't really see a reason to change from what the default recommendation is. That actually kind of goes right in line for Transmodeler as well. They had, there's a time-based, but similar kind of thing. Their distribution was pretty close to what our distribution was. So yeah, it's same information here, just kind of more of a validation of the default values rather than a recommendation for change. So the next two would be acceleration and deceleration. And there are, I guess, a lot of ways you can modify this in the software. We weren't really targeting to modify the default values, so what the vehicles can or cannot do, but we were more looking to modify it in terms of the driving behavior values. So these values of CC8 and CC9, so standstill and acceleration from 50 miles per hour. So to do that, we took all the accelerations from the trajectory data at different locations, so separated them out based on vehicles that were at a standstill, so either at a ramp entrance or at a signalized intersection or entering the freeway from a ramp. So that was kind of standstill versus kind of getting up to speed. So going from that 30 or 40 miles per hour, 50 miles per hour up to the 65 or 70 miles per hour. So you can kind of see the graphs here. Again, our teal lines are the observed data, and we kind of took the high end of that. So there's a ton of data you can see obviously in the standstill that is really on the low end, and it's pretty hard to determine how many of those data points are being blocked by something upstream, whether that's another vehicle or a subsequent light or just other obstructions that are not just pure acceleration. So kind of looking at the maximum values, we had a few out here in like the 9 feet per second range, and then a few in the 4s. So these are just slight deviations from the default values, but I think it does kind of tone down the model a bit and make things less aggressive when they're applied. So and in general, that was kind of our observation. Just Vissim and Transmodeler modeling in Kentucky. Kentucky drivers are pretty forgiving and are not overly aggressive typically. So usually we are needing to kind of hamp down models to calibrate them and make them more accurate to what's going on in kind of the real world conditions. So moving to deceleration, similar, we weren't trying to really impact what the vehicle's capable of, but more of what drivers are likely to do. So looking at kind of the lane changing behaviors and the driving behavior components. So this is just kind of two curves here. You can see that the light blue is freeway decelerations and the purple is arterial decelerations. So just graphing that on kind of a cumulative percentile basis. And then I overlaid kind of the Vissim defaults over that. So if you think about it, the Vissim defaults are pretty close to probably what you'd expect. So accepted deceleration, what you're likely to do is probably in that 35th to 50th percentile, which really makes sense and driving, when you're driving, you're likely to do probably 30, 1/3 or a half of the deceleration that you could do, just to kind of facilitate maneuvers. And then if you had to kind of allow somebody to get in or allow somebody to make a lane change due to whatever conditions, you're probably willing to go down a little bit further. Not really willing to slam on your brakes, let's say, but slow down to facilitate that move a bit more. So that's kind of in that 75th to 85th percentile range. And then looking at kind of the maximum deceleration, that's really in that 90th to 95th percentile range. So we kind of felt that the Vissim defaults are lining up pretty closely with probably what you'd anticipate. And so we use those percentile ranges to develop values that we're recommending in the guidance, of which these default values kind of fall in the middle. So the ranges we're recommending are similar to, but not exactly the same as the Vissim defaults. And honestly, that's both to kind of help and in some ways, hopefully, control the way that models are developed so that we don't have people making large scale edits to accelerations and decelerations to facilitate weird conditions in a model that might not be noticed in kind of existing, but then extrapolated out, kind of make bigger impacts. So jumping ahead here, the standstill distance. This was one that the default value is a little bit hidden, but it's this dashed red line kind of hovering here. The default in Vissim is a kind of a fixed distribution, and the average is at 6 and 6.56 feet or 2 meters. And so our data is this, again, light blue kind of jagged line with the dots. And so we wanted to widen that out or expand that distribution a bit. And so for our project, we were trying to figure out how to do that. Like I said, Transmodeler is also part of the study. Transmodeler, you can edit the average, you can edit the standard deviation and max and min. So it gives you more to edit. And we were looking for something similar in Vissim. So brought that up with PTV and we're talking with them about it, and they presented this pretty good idea to kind of to force it in with multiple distributions. So we didn't want to make it overly complicated because people have to, we're hoping that people will do this in their models. So we decided to try to use 3 different distribution curves. So you can see them like the light green here, and apply them at different ratios to the vehicle compositions. So using, I think, versions Vissim 11 and on, hopefully people are using the newest versions. You can add multiple distributions to Wiedemann 74 and then apply them at different ratios for the vehicle compositions. So doing that, we could set different averages, and ultimately we were able to get kind of this green curve. Not exactly perfect, but a pretty good representation of our collected data. And it also gives you more to manipulate. So if you think you have a corridor that people are sitting a little tighter, you could move it in or you could move it out if they're sitting further away. So it gives you more variability and a greater range. So that's really standstill distance. Lane change distance, this one was probably the most difficult to use the trajectory data for, just because you want to observe when people are changing lanes to make a turn or take an exit. But the trajectory drone data, even just based on FAA regulations and waivers that we could get, we could only fly the drone so high to also get resolution that would work. And so we have a few extra flights that were looking down a corridor or along a roadway, And those actually were extremely useful for this kind of thing, just kind of anecdotally observing, okay, this vehicle took, made the exit, or this vehicle turned left, but where did it start, and what lane was it in when it came into frame, or how far back was that, and knowing just in Google Earth you could measure. We pretty much observed that nobody was really changing lanes within, let's say, 1,000 feet or so, and most people were well in their lane further back than that. So people were starting to change lanes maybe in that 1,000 to 2,000 foot range, but a lot of people were in the lane they wanted to be in well in advance of that. This is mostly on freeway segments, but that's where it seems to be most critical anyway. So the default value, this is something that when I'm reviewing a model, I see changed probably the most, or I guess I don't see changed and I'm looking for it to be changed, is the default value is 200 meters or 656 feet, which is pretty tight, obviously, on a freeway section, and maybe is okay for some arterials and downtown grid networks. But kind of based on that observations, we didn't exactly land on this is the end-all be-all distribution, but wanted to provide a good starting point. So we were looking at the defaults in Transmodeler and felt that those are pretty good for just kind of if you had nothing else to go on, applying these values. It should be noted that kind of in the guidance document and throughout each section of the guidance and all of our presentations and discussions with other consultants and with KYTC, we are recommending that kind of if you have a local knowledge of a project, that kind of supersedes any of these values that we're providing. So certainly if you know that you're modeling a network where a lane changes, everyone gets in the right lane to exit a mile and a half in advance, then that's what you should be kind of programming. But these are just to provide kind of, again, like a base to get started and to kind of bring all the models closer to center. So yeah, I'll move on to the next one. And this is, sorry, I should have changed slides, but this is, again, pretty much all that I was discussing, with the exception of, I guess, using later versions of Vissim, you can apply a distribution. So you don't have to give it strict values, but you could enter a distance distribution in that kind of database and then apply that to your link segments and connector segments as it makes sense. So the next ones are vehicle speed ranges. So travel speeds on the roadway. This graph is a pretty good illustration of what the default values are in both software packages for something like a 70-mile-an-hour freeway, and then based on our observed data, what we would recommend it to be. So we got samples from 50 different roadways of varying context, speed limit, facility type. So I think on the next slide I showed this, but we developed speed ranges for kind of urban and rural roadways. So urban and rural speed ranges for these miles, different speeds and posted speed limits, and then for different roadway types. So we got enough data to be able to recommend those, and those are the most common speeds that we're kind of modeling or that we have throughout the state. Just jump back here to the freeway segment really quick. But for each one, we wanted to have a multi-point curve, so kind of a distribution of 10 data points, so each 10th percentile. And this also helped really kind of hamper down the models. We're slowing the models down for the most part in all cases at all the different speed limits. I don't know if that's just a general attribute of the way that people drive. Again, Kentucky drivers are on a 70-mile-an-hour roadway are not going that far above 70. or if, so it's hard to say if that's just a local observation or not, but it seems to be similar across the board. You can see on these freeway segments, we're kind of hampering it down from both Vissim and transmodeler, but on these arterial segments, we're actually expanding it a bit more to provide more variety and variability in travel speeds. So instead of vehicles just trying to go between like the 44 and 48, we're actually showing vehicles that are going in the 30s up into around 60 or so. Yeah, this just added another level of variability and control to the models to kind of better distribute the traffic. Vehicle fleet composition, at least again for us and for me, reviewing models is something I observe often, that this is unchanged. It'll just be either just the default or the Vissim US fleet default, which actually matches the Kentucky data pretty closely, but or just kind of a very simplified vehicle mix. Someone adds a few 2 or 3D models, and then 1 or 2 cars, 1 or 2 trucks, and then creates a custom mix from that. That's not really representative of what's going on. So we wanted to capture that by taking what vehicles are actually in the state. So using the VIN database, we were able to kind of see that. And the one issue here is that you can see that the trucks are tractor trailers and single unit trucks. So the orange here are not as represented in the Kentucky average. Trucks are usually traversing through. And so we created this graph, but really we ended up creating a little interactive spreadsheet tool that, if you collected data on a route or in an area, you could program in, okay, I have 93% passenger vehicles and 70% trucks, and it would auto update with what the then percentile breakdown should be to best match the Kentucky data, considering all the VIN registration data for passenger cars. So I guess, again, like I said, if I'm reviewing a model and I saw somebody loaded in the US fleet, I wouldn't be too upset about it. It's very close to the Kentucky average, so which is great. But I think knowledge of the US fleet file existing and it being kind of readily available to everybody who kind of has Vissim loaded on their machine seems to be limited. We presented this before, and people kind of came up afterwards asking me about, well, okay, I liked what you were saying, but I don't know how to get access to that. I don't think I have that on my computer. And so so just kind of talking about that or adding that in. And then again, transmodeler, not as close, but really the mix there is kind of between the pickups and SUVs and middle performance passenger cars. So just kind of adjusting that mix a bit would probably get us pretty close. And then the last one is the truck weight to power ratio. This one was the least local, but we wanted to try to look at this in terms of how it affects the models with regard to truck accelerations and decelerations. That's really the biggest piece to that. So just noticing that sometimes trucks will kind of beat a passenger car from a standstill in Vissim. And so at least from our experience, it's not always the most realistic thing. I mean, unloaded truck has a lot of power, but a loaded down truck certainly doesn't. So we wanted to kind of explore that, and we looked at some research, which is most of these curves are based off of that research. And then the Vissim default is the lighter green. I know there's a jumble of lines there, but the lighter green dashed line is the Vissim default, and the transmodeler default is the kind of darker green. And so based on our knowledge, Vissim is by default applying the distributions of weight and power randomly based on a range of values, which creates kind of higher ends and lower ends. So these two spikes here and that's really kind of due to the caps on the upper and lower limits. Those caps kind of then get extrapolated out, multiplied against each other. So we kind of are proposing kind of maybe a more rounded curve distribution, and that would be kind of, again, hampering just down those accelerations. That's our main focus of that, but this would maybe be a more realistic flow of vehicles that are still fully loaded and unloaded, but then a lot of vehicles that are in the middle there. So that was probably a ton of information. Hopefully that makes sense to people that are modeling or have modeled, and provides kind of an overview of maybe a different way to look at how to get parameter values or get parameter ranges using a different set of data, or kind of going pretty in depth. That was an aspect of the project that we were really interested in making sure that we kind of researched thoroughly and got right. A lot of what we're recommending is similar to, you saw, it's close to the defaults in a lot of ways. It's also similar to what a lot of other states are recommending. It's just good to kind of know that that's validated in some ways by data observations. So it is close to real world conditions as far as we can tell. But kind of to wrap things up, I just want to hit on the deliverables for our project. So all this work was done to create a guidance document for modelers and for reviewers and just users of microsimulation throughout Kentucky. So that's the main deliverable, is the finished guidance document, kind of currently under final review, and hopefully will be completed here in the next month or so. But that would contain all of our recommended parameter values and ranges. And then in addition to that, we've created some seed files. So for both Vissim and Transmodeler, files that people can use, similar to maybe the US default fleet mix, where they could start a file from there, and that would have a lot of the things preloaded in, or if they have an existing file, they could import a lot of the variables to their existing file and modify it accordingly. In addition to a lot of this parameter work, we did want to kind of try to validate it and use it in a practical way. So we did some pilot projects, which Rob kind of hit on in the beginning. So the summary and results of that will be kind of included in the guidance document and is a separate kind of presentation. But overall, the pilot projects, we just picked a few of those microsim files that we reviewed in the beginning, and then reran them, took their results from the files that were submitted, applied the recommended values that we came up with, reran it, and then on a few of them, I also just kind of cleared out everything back to the software defaults and ran it again. And so we're trying to compare those three things, and kind of overall, the pilot kind of proved that this effort of creating parameters and values was worthwhile. It got us close. It's not a one size fits all. It didn't work in every occasion, didn't get us to a perfectly calibrated model, but that wasn't really our goal. We were just trying to kind of pull everyone closer to center and kind of ease that last step in the calibration. So aside from starting from nothing, or starting from commonly what I would do here is find an old project that I thought went pretty well. Maybe I'll pull that up and start from that file and then make edits accordingly. But that's a file that I made or somebody else made, and so this would be a set that everyone could use. So yeah, in some cases the recommended ranges got us a little bit closer to real world conditions than it seemed like the actual submitted files were, and in other cases it seemed like it got us close but not all the way there. So yeah, and then the last aspect, I guess, is the training that we're going to do. So for kind of people in Kentucky that are working on Kentucky projects, this will be kind of a best practices and an implementation of the parameters. So we're planning to do that training toward the end of this month, but that kind of wraps up all of the project objectives and deliverables. And so that should be completed in, hopefully September, but potentially October. And the guidance document will be rolled out for use.